Complex numbers were first realized and developed during the 16th and 17th century. Earlier, mathematicians dismissed negative numbers since they were thought to lack any real meaning. It's not very surprising that mathematicians at this time had an even more hostile approach to the root of a negative number, what today is known as an imaginary number. If arithmeticians were murdered because of the infinite irrational numbers, such as pi, there must have been a special tension while they worked with an imaginary number that could be written down but didn't exist. However, there was one man, Cardanos, who foresaw others when he solved a cubic equation that included the square and cubic root of a negative number. Even though he didn't realize the true properties of these numbers, he certainly created the groundwork for generations to come.
Later on, the imaginary unit, which was coined by Carl Friedrich Gauss, I, was determined to, according to I squared equals minus 1, which quickly reduces to I equals to square root of negative 1. Even though this looks like a bunch of crap without any physical reality, the introduction of I made it possible to at least move imaginary units around with an equation much easier. At the same time, equations with real answers, the imaginary unit cancelled out and left a much more comprehensible answer. Calling it I equals square root of minus 1 doesn't really change a bit, but perhaps for obvious reasons, mathematicians like to just string things in close than to make it look like there's one simple variable. So, to sum it all up, the unit I, it was from time to time called a mathematical rainbow unicorn. We sure can describe it, but that doesn't make it any more real.
All real numbers can be explained along an ordinary number line, or also known as the real line. Some real numbers, like 1/3 or 1/7 or pi, can be exceedingly hard to place out accurately, but rest assured they are there. If the real number line were to represent the x-axis, the y-axis would be accounted for by the imaginary line, which consists of roots of negative numbers or units of I, if you will. So, for example, we have I, 2I, 3I, minus I, minus 2I, and minus 3I on the x-axis. Now, this area created by the real x-axis and the imaginary y-axis creates a plane, a two-dimensional plane known as the complex plane. Any point that is placed out along the real axis is, of course, a real number, and any point placed out along the y-axis, the imaginary axis, is, of course, an imaginary number. And complex numbers are points somewhere in the complex plane, consisting of a real part and an imaginary part. This leads to the complex number and its shape, the form which we use to express complex numbers, and it comes in the shape of A plus BI, where both A and B are real numbers and I is, of course, the imaginary unit. And A describes the position along the real x-axis, and B explains the position along the y-axis, and I is the imaginary unit. So, an equation has a complex solution when you end up with a root of a negative number accompanied by a real solution. This often occurs when p divided by 2 squared minus q is smaller than 0, and since you probably recognize this part over here, coming directly from the PQ formula, and more exactly from within the root of the PQ formula, you can quickly jump to the conclusion that if this thing is smaller than 0, and thereby a negative number, you will end up with the root of a negative number, which is impossible to describe with real methods.
Now we're going to solve a problem with the help of I. And since we want the x alone, we will take the square root of both sides, which will be equal x equals square root of minus 25. Now this can be rewritten as x equals square root of square root of 25 times minus 1. And the minus 1 comes from I squared. And next step is x equals square root of 25I. And this can be rewritten also as x equals square root of 25 times the square root of, square root there, or yeah, square there, and I squared. And the answer will be plus minus, since we took the square root of 25, we're going to have a 5 that's plus minus, because you don't know, you can get two answers, a positive and a negative, which will lead to a plus minus 5, and then times I. And this will be our answer.
Cardanos problem. If you take the number 10 and you divide it in two parts, and then you multiply those parts with each other, and that should be equals to 40. So let's see. We have the first part with x, and the second part, yeah, we can call it 10 minus x. And all this should be equal to 40. So let's see. We have 10x minus x squared equals to 40. So now we see, before we can apply it to the Deeqa formula, we must make this x squared positive. So we can divide everything by minus 1. And that makes my x squared minus 10x equals to minus 40. And if we move it around, we move it over, so we get x squared minus 10x plus 40 equals 0. Now we should apply it to the PQ formula. See, we have minus 10 of x equals minus 10 divided by 2 plus minus square root of minus 10 divided by 2 squared minus 40. X equals 5 plus minus square root of 25 minus 40, and it's equal to x equals 5 plus minus the square root of minus 15. And now we should solve it with the help of I. So first, x1 is equal to 5 plus minus square root of 15I squared. Since I squared is equal to minus 1, and we can write the square root of minus 15 as the square root of 15 times minus 1. And that's the same thing as I. So this is the first answer, and we get x1 is equal to 5 plus minus square root of 15I. And the next answer is, of course, x2 equals to, no, it should be plus, right? And equals to 5 minus the square root of 15I. And now we got answer on Cardanos problem.
Okay, one last problem. X squared minus 12 plus 100 equals 0. We're going to try to solve this problem, and perhaps a complex answer will appear. So our first step, if we choose to apply the PQ formula, is to apply the numbers and exchange the P's and the Q's to bare numbers. So we begin with x equals minus 12 over 2 with a reversed sign plus minus the root of minus 12 over 2 squared minus 100. And then we simply simplify this. This simplifies down to 6 plus minus. We get 12 divided by 2. Minus 12 divided by 2, that's minus 6. Minus 6 squared is 36. Minus 100. And all of this reduces down to 6 plus minus 36 minus 100 is 64, the root of negative 64. Now, if you want to continue solving this problem, we have to implement I, and we can easily see that the root of minus 64 equals the root of 64 times minus 1, and this reduces down to the root of 64, positive 64, times the root of I squared. And what we're left with is 8, the root of 64 is 8, and the root of I squared is just I, so we get 8I. And since all of this is the same as this, we can put them together and we get x equals 6 plus minus 8I. If you continue on our last problem that we solved, we got the answer 6 plus minus 8I, and this is the answer in rectangular form. Now, if one would like to have the answer in polar form, you would have to convert it. Now, if you remember, polar form is the angle against the x-axis combined with the length of the vector. Now, it's very simple to convert between these two forms of expressing a complex number. And in this case, we have it in rectangular form, and this can, with this information, we can create a right triangle with the length 6 along the x-axis, the real part, and the length 8 along the imaginary line. Now, using simple trigonometry, we can find out the length of the hypotenuse, and we can find the angle against the x-axis. Now, to begin with, we try to solve for the hypotenuse, and if we want to do that, we use the Pythagorean theorem. And if you recall, it's 6 squared plus 8 squared equals x, and let's say the hypotenuse length is x squared. So what we get is 36 plus 64 equals x squared, and 36 plus 64 is 100. And if x squared equals 100, x must be the root of 100, x is plus minus 10. And since we're talking about length, the negative really isn't that interesting. So the hypotenuse is 10 units long. Now, we have the length of a hypotenuse, and we want to calculate the angle against the x-axis. Then we could use tangents perhaps, and what we simply do is the tangent for the angle y equals 8 over 6, the opposite over the adjacent. And if you want to simplify this, you simply multiply by the invert tan on this side and do the same with the invert tan on this side. And what you're left with is invert tan 8/6 equals y. And if you do a little simple calculation, you find that y equals